Okay, in this video, we're going to look at some different examples and applications of the scalar product. Okay, one application of the scalar product is what we call work. Now, we're going to look at work in much more detail later in the semester, but ultimately work is simply a product of a force with a displacement. And you could imagine, for example, I have this box here, and there's a rope, and I'm pulling on the rope, and as I pull upward on the rope, there's some component of the force along the floor, parallel to the floor, and so the box slides across the floor. Now, if I pull up with enough vertical force, the box would lift off the floor, but generally when you're pulling a box, you're just pulling it so that it slides across the floor. And so we could imagine that if I take a vector f, I can break it into a component that is parallel, so that would be f parallel, and a component that is perpendicular, that would be f perpendicular. And if we look at this situation, only the part of the force that's along the displacement is affecting the motion in that direction. This vertical force is lifting up against the weight, but it has nothing to do with the left-right motion of the box. And so only this parallel component of the force contributes to the work. And so what we would say is that the work is the product of this displacement with this parallel component of the force. But what's that? That's the scalar product of the original force with the displacement vector. So force times distance, yes, but it's the component of the force along the direction of the motion. And we're going to see that this concept of work has many, many different applications in physics. It's a very important idea. But in order to actually calculate the work, you take the scalar product. And so my point here is that all this math that we're doing with vectors, it's not just this abstract thing that doesn't have meaning. All of these things have definite connections to the physical world that we're living in, and they're an intrinsic part of physics itself. So I've got a few other things that we can use the scalar product for in physics. It can be used to calculate energy, which is related to work, and power, which is related to energy. It's used in the study of electricity to determine forces acting on distributions of electrical charges. It's used in the study of the motion of fluids, like, say, water flowing down a pipe or something like that. It's used to calculate the flux of vector fields, which is very useful in the study of both electric and magnetic forces. So we're going to see that all through physics, this scalar product comes into play. So we need to be able to use it and calculate it. So let's look at some examples of doing that. Here's our first example. We have calculate the scalar product for two vectors. We've got vector A, which is 6i hat minus 3j hat plus 3k hat. We've got a vector B, which is 3i hat plus 2j hat plus k hat. And so we want to take the scalar product of A and B. So how do we do that? Well, we know that we take the x components and multiply them together. So 6 and 3. We can see right here we've multiplied together 6 and 3. Then we're going to take the y components. That's going to be minus 3 for the j and 2 for the j. And so we're going to multiply those together. That's minus 3 times 2. And then finally we have 3k hat. And we have over here on vector B, we have just k hat. That's going to be 3 times 1. And we see that there, 3 times 1. So we multiply together the x components, and we multiply together the y components, and we multiply together the z components, and then we add all of those together. And so we've got 6 times 3 gives us 18, minus 3 times 2 gives us minus 6, 3 times 1 gives us positive 3. So we add all these together, and we get the scalar product A dot B is equal to 15. And that's just it, 15. Notice, it's not 18 I hat minus 6 j hat plus 3 k hat. There's no I hats, j hats, or k hats. That's the most common mistake I see my students make when they're trying to do the scalar product. They want to put those unit vectors back in. But there are no unit vectors. Why are there no unit vectors? Because it's the scalar product. and the answer is just a number. It's just 15. All right, here I've got two vectors. I've got a vector A, which is 4x hat minus 1y hat plus 7z hat, and a vector B, which is 2y hat minus 3x hat plus bz in the z hat direction, where bz is just a variable because we don't know what bz is yet. It's just an unknown thing. Now, there's a couple of things here that I want to notice. I was a little sneaky in the way I wrote this. This is 2y hat. I rewrote this. This is a perfectly valid way to write it, but it's not the usual way. So if you start calculating scalar products, you might start to go 4 times 2, then minus 1 times minus 3. And can you see how I would have tricked you if I did that? Because what would you multiply together? You want to multiply the x parts together. So the 4 is going to go with the minus 3. The minus 1 in front of this y hat is going to go with the 2 here. So make sure that you're multiplying together the correct terms when you're taking the scalar product. That's the first tricky thing about this problem. You have to pay attention to that kind of thing. The second tricky thing that you have to pay attention to is what this means, this BZ. It's an unknown. If I wrote this problem out and I said A is equal to this vector here, and B has an x component of minus 3, a y component of 2, and a z component that's unknown, you might not know what to do with that. But all you do with that is you just write it out. I've got some variable. This is unknown, so I put a variable in place of the unknown thing. So anytime you're working a problem and you don't know something, think about just expressing it as some variable and seeing if you can do some math and solving for that unknown variable. So we haven't even actually stated what this problem is. This is just some preliminary stuff I wanted to go over. But what's the actual problem? The actual problem is this. We've got these two vectors. One has this unknown component bz, that's the unknown z component, and I want to determine the value of bz that makes these two vectors perpendicular. How the heck are we going to do that? Well, here's our key insight. Perpendicular vectors have a scalar product equal to 0. So what does that mean? It means if I take the scalar product of A dot B and I set it equal to 0, then A and B must be perpendicular. So that's what we're going to do. We're going to take the scalar product of these two vectors, we're going to set it equal to 0, and then we're going to solve for the unknown component BZ. So here I've written these out, and I wanted to point out again, the way that I've written these vectors is a little bit sneaky. The x and the x go together there, the y and the y go together there, and then the 3 and the bz will go together when I take that scalar product. So here what I've done is I've taken these two vectors and I've rewritten them so that they're in the more usual way. I've got 4x hat minus y hat plus 7z hat, and then for the b, I've put the x hat in front, which is the usual way to do it. I've got minus 3x hat plus 2y hat plus my unknown bz in the z hat direction. I take the scalar product together, so I multiply together the x components, 4 times minus 3. You can see I've done that right here. That's going to give me minus 12. Here I've got minus 1 times 2, and so that's going to give me minus 2, minus 1 times 2. And so then I've got plus 7bz. That's the scalar product. And since these two vectors are perpendicular, I know they're going to equal to 0. And so here I've got minus 12 minus 2. That gives me minus 14 plus 7bz equals to 0. And so if I solve this for bz, I get that bz is equal to 2. In other words, that's the value of bz that makes the scalar product equal to 0. And also, that means that's the value of bz that makes these two vectors perpendicular. So you can write in your notes, that's the value of bz that makes these vectors perpendicular, or makes the scalar product equal to 0, which effectively is saying the same thing. Now, here we have a third example, example 3, And this example tells us, using the scalar product, determine the angle between the following vectors. And so we have the vector A, which is 5i hat minus j hat plus 3k hat. We have the vector B, which is 2i hat minus 3j hat plus 4k hat. So what are we going to do to find the angle? Well, we know the relationship A dot B equals A magnitude B magnitude times the cosine of the angle between them. That relationship is from the definition of the scalar product. That's how the scalar product is defined. And so if I solve for the cosine of theta, I find that the cosine of theta, I'm just going to divide both sides by A magnitude times B magnitude, and I end up with A dot B divided by A magnitude and divided by B magnitude. And so if I want to calculate the cosine of theta, I just calculate the value of the scalar product, which we just saw how to do in the previous examples, and then I want to divide that by the magnitude of A and the magnitude of B. So we've already seen how to calculate A dot B. That's just going to be a number, a scalar, and so that's going to be 5 times 2, that gives me 5 times 2, plus minus 1 times minus 3, that's what you have right here, plus 3 times 4. And when you multiply all of those out and add them together, you get 25. So the scalar product of these two vectors is 25. Now I want to take that 25 and divide by the magnitude of A and divide by the magnitude of B. So let's recap here. We've got A dot B equals 25, where A is these two vectors. We can calculate A magnitude using the three-dimensional Pythagorean theorem that we learned in one of the previous videos. And so we just take each component, square it, add them together, and take the square root. So the magnitude of A is going to be 5 squared plus minus 1 squared plus 3 squared. That's going to be 5 squared gives me 25, plus 1 plus 9. And when you take the square root of all of that, you get 5.91. Similarly for B, you've got 2 squared here, 2 squared, minus 3 squared, and 4 squared. And again, just to point out, when you take this minus 1 and square it, minus squared becomes positive. Same thing down here, the minus squared becomes positive. And so now I can plug in. I've got A dot B is 25. I'm going to divide that by the magnitude of A, which is 5.91. Divide that by the magnitude of B, which is 5.38. Now, that thing in the parentheses, that would be the cosine of theta. To get theta, I take the arc cosine. And so theta is the arc cosine of this thing in the parentheses here. And when you take that, you get 38.1 degrees. So that 38.1 degrees, that's the angle between the vector A and the vector B. Now, on this last side, I've summarized some of the properties of scalar products. You can find proofs of these. They're not that hard to prove, but I just wanted to show you some of these things so that if you see them, you'll know how to do them. So the first thing that we can note, the first property is that the scalar product is commutative. We've already seen that. A dot B is equal to B dot A. Now, if I have two vectors that have added together, B plus C, and I take the scalar product of that sum with the third vector, in this case A, you just distribute the A and the B and the C normally. So this becomes A dot B plus A dot C. So you just do a normal distribution here. Now, if I take A dot SB plus C, where S is some scalar, I can just factor the S out in front. And so I distribute this the same way, and this becomes S times A dot B plus A dot C. Similarly, if I've got some S1A dot some S2B, I just factor out the scalars. That's why it's an S, because these are just regular numbers. And so that leaves me with A dot B times the product of those two scalars. We've also already seen two vectors A and B are perpendicular. I don't know if you've ever seen this math symbol before. It's an if with an extra F. That's a math shorthand. It means if and only if. So two vectors A and B are perpendicular if and only if their scalar product A dot B is equal to 0. We've also seen that if I take the scalar product of a vector with itself, the angle between a vector and itself is 0. And so that scalar product is going to be A magnitude, that's the magnitude of the first, times A magnitude, that's the magnitude of the second, times the cosine of the angle between them, or the cosine of 0. That is, of course, 1. The cosine of 0 is 1. So I get A magnitude times A magnitude, which is A magnitude squared, which is just going to be the scalar A squared. So if you see A dot A, that's just going to be A squared, where A is the magnitude of A. Finally, taking derivatives. If you take the derivative of two vectors that are undergoing the scalar product, you basically use the product rule. And I could be differentiating with respect to x, I could be differentiating with respect to time, it doesn't matter. I'm taking the d whatever of this scalar product, and so it's the first one, A, times the derivative of the second one, B, plus the derivative of the first one times the second one. You will, of course, recognize that's the scalar product from calculus. Now, actually proving that from vectors, it's actually not that hard. I'm not going to waste your time doing it. If you're really curious, send me an email or come by my office hours and I'll show you the proof or send you the link to a proof. But I think basically I just want you to remember that if you need to take the derivative of a scalar product, you use the product rule. All right, well, that's it for some basic applications of the scalar product. We'll see some more as we go throughout the course, but at least this should be enough to get you started.